Hello everybody. We are excited to present our work on sample-efficient reinforcement learning with stochastic ensemble value expansion. Stochastic ensemble value expansion, or STEVE, is an approach to deep reinforcement learning that merges model-based and model-free techniques. We use bootstrapped ensembles of neural networks to maintain uncertainty estimates, and use model-based reinforcement learning only when we are confident in the predictions made by our dynamics model. This allows Steve to match or surpass the performance of model-free approaches, even in challenging environments where our dynamics model makes significant errors. First, some background. Deep Q learning uses a deep neural network to approximate the total future reward of taking an action. Once such a Q function has been learned, we can construct a policy by taking the action which maximizes the Q function in any given state. DDPG expands this to continuous action spaces by learning a neural network policy that computes an approximate maximum for our Q function. In order to improve our Q function's estimates, we sample interactions from the real environment and update our prediction of the return for each state-action pair to be more similar to the observed return. One approach to model-based reinforcement learning, model value expansion, improves the target of this update by using a learned dynamics model to simulate the effect of following the current policy for additional time steps. If the dynamics model is accurate, model value expansion will lead to better targets and faster learning. However, approximation errors in the dynamics model can cause the opposite effect. The targets become incorrect, making learning a Q function very difficult. In complex environments, where model errors are almost guaranteed, model-based rollouts can do more harm than good. Steve aims to address this issue. We replace both the Q function and dynamics model with an ensemble of neural networks, which have different initializations and train on different mini-batches at each step of training. By consulting various ensemble members, we can predict multiple Q targets for each rollout horizon, which allows us to compute an uncertainty estimate. In other words, if after some number of model rollout steps, the various predictions of the ensemble members more closely agree, then we are more confident that the prediction is correct at that horizon. We compute our target as a weighted average of the targets at different rollout horizons, assigning high weight to horizons with high confidence. We evaluated our approach on a variety of continuous control tasks. Code for all evaluations is available online. We found Steve to consistently match or outperform baseline algorithms, including vanilla DDPG and model value expansion, while being significantly more sample efficient. Despite the increased computation per update, Steve was also equal or better than the baselines in terms of wall clock time. We also showed that Steve performs better with longer horizon lengths, and performed ablation experiments to isolate the gains in performance. In summary, we introduced Steve, an uncertainty-aware reinforcement learning algorithm. Our technique for merging model-based and model-free approaches leads to high performance and sample-efficient learning. Future directions include exploring more complex world models for various tasks and comparing different techniques for estimating uncertainty. For more information, please do check out our paper or attend our talk on Thursday, December 6th at 4:25 p.m. Thank you.